Hello students, I, Trupti Patel from Arihant College of Arts, Commerce and Science. Students, today we are going to study ionic equilibria. First, let us study introduction. The equilibrium between ions and unionized molecules in solution is called ionic equilibrium. The principles of chemical equilibrium we studied in standard 11 will be applied to ionic equilibria. In this chapter, with the help of the principles which we have studied in 11th standard, we'll determine equilibrium constant and concentrations of ions and unionized species. In particular, examine the following ionic equilibria. These are the points: H plus and OH minus ions and unionized water molecules, ionization of weak acids and weak bases, reactions between ions of salt and ions of water, and solid salts and its ions in water. Students, in 12th standard we are going to study in details. In 11th standard we have studied the principles of ionic equilibrium. Types of electrolyte. Now here we are quite familiar with the word electrolyte, electrolysis, right? So the types of electrolyte we are going to study. The substances which gives rise to ions when dissolved in water are electrolytes. The non-electrolytes are those which do not ionize and exist as molecules in aqueous solutions. The electrolytes are classified into strong electrolyte and weak electrolyte. Now, this classification is based on their extent of ionization in dilute aqueous solutions. First, strong electrolyte. The electrolytes ionizing completely or almost completely are strong electrolytes. So in strong electrolyte, they ionize completely. We get complete ions. For example, strong acids, strong bases, and salt. Here we can quote an example, NaCl. When you take salt and mix it, when you dissolve it in water, you get complete ionization. So you get Na plus ions and Cl minus ions. Next, weak electrolyte. The electrolytes which dissociate to a smaller extent in aqueous solution are weak electrolytes. Weak acids, weak bases belongs to this category or to this class. Weak electrolyte dissociate only partially in dilute aqueous solutions. An equilibrium thus can be established between the ions and non-ionized molecules. The ionization reaction, there it is represented as double arrow. You can see in the bracket, the upper arrow is going in the you can see a forward arrow, and down you can see the backward arrow. So this is called as double arrow between the ions and non-ionized molecules. Degree of dissociation. The degree of dissociation of an electrolyte is defined as a fraction of total number of molecules of the electrolyte that dissociate into its ion when the equilibrium is attained. This alpha, you can see the sign. So that sign is called as degree of dissociation. So this degree of dissociation has a correlation with electrolyte, that is strong acid, strong base, weak acid, weak base. It is denoted by the symbol and it is given by, so you can see the degree of dissociation is equal to the number of moles dissociated divided by total number of moles. Percent dissociation. Now if you want to find percent in the form of percentage, so percent dissociation is equal to degree of dissociation multiplied by 100. Now suppose if C is the molar concentration of an electrolyte, the equilibrium concentration of cation or anion is, you can see in the bracket, degree of dissociation multiplied with C molar concentration moles upon dm cube. Now when we study electrolyte, non-electrolyte, we have studied degree of dissociation. So there is a definitions given by acids and bases. Here we are going to study definitions given for acids and bases. So acids and bases are familiar chemical compounds. Acetic acid is found in vinegar, citric acid in lemons, magnesium hydroxide in antacids, ammonia in household cleaning products, the tartaric acid present in tamarind paste. These are some acids and bases we come across in our day-to-day life. So now we are going to study the definition for acid and bases given by Arrhenius theory. According to this theory, acids and bases are defined as follows. Acid. Acid is a substance which contains hydrogen and gives rise to H plus ions in aqueous solution. For example, HCl. Now students, you can see a small bracket where we have written AQ. AQ means aqueous solution. Now HCl gives you H plus ions plus Cl minus ions. Second example, you can take CH3COOH, that is acetic acid. Acetic acid gives you CH3COO negative plus H plus ions. In the first example, you can see single arrow. In the second example, you can see double arrow. In both the examples, you can see in the product H plus ions. So Arrhenius described H plus ions in water as bare ions. They hydrate in aqueous solutions and thus represented as hydronium ions H3O+. We herewith conveniently represent them as H plus ions. So, in short, students, acid defined by Arrhenius, according to Arrhenius theory, is we should have H plus ions. If you see H plus ions, it is acid. Bases. Base is a substance that contains OH group and produces hydroxide ions, OH minus ions in aqueous solutions. For example, NaOH aqueous gives you Na plus ions plus OH minus ions. In the second example, NH4OH gives you NH4 ions plus OH minus ions. Now, according to Arrhenius theory, base means you should have OH minus ions. So, in both the examples, you can see OH minus ions in the product. So, Arrhenius theory accounts for properties of different acids and bases and is applicable only to aqueous solutions. It does not account for the basicity of NH3 and Na2CO3, which do not have OH groups. Second, Bronsted-Lowry theory. According to this theory, acids and bases are defined as follows. Acid. Acid is a substance that donates a proton, that is H plus, to another substance. Base. Base is a substance that accepts a proton from another substance. Let us take an example. HCl. HCl is an acid. So, below HCl we are going to write acid. HCl plus NH3. NH3, that is base. So, below NH3 we are going to write base. So, when you mix them together, it gives you NH4 plus ion plus Cl minus ions. So, according to Bronsted-Lowry, an acid donates a proton to another substance, right? So, what is acid? Acid donates a proton to another substance. In this, HCl is an acid. Now, in this, H plus ions will be donated to another substance, and the base is that which accepts a proton from another substance, right? So, HCl acid 1, NH3, it's a base. It gives you NH4. So, NH3 accepts one proton and it gives you NH4 plus Cl minus. So, NH4 acid 2, Cl base 1. In the above reaction, HCl and NH4 are proton donors and acts as an acids. They have proton, they can donate proton. So they are proton donors. NH3 and Cl are proton acceptors and acts as bases. Further, it follows that the products of Bronsted-Lowry acid-base reactions are acids and bases. The base produced by accepting the proton from an acid is the conjugate base of that acid. I'll repeat, students. This is very interesting and important. The base produced by accepting the proton from an acid. So acid is what? It gives a proton, right? It has a proton, it is going to give away the proton, and the another should accept the proton and will become base. So the base produced by accepting the proton given by an acid is the conjugate base of that acid. Similarly, likewise, the acid produced when a base accepts a proton is called conjugate acid of that base. A pair of an acid and a base differing by a proton is said to be conjugate acid base pair. I'll repeat, students. A pair of an acid and a base differing by a proton is said to be conjugate acid base pair, right? A reaction, you can see the reaction, how there is conjugate acid base pair. HCl, right, students, is an acid as we have seen in that example, plus HCl in an aqueous, right, plus H2O. In the bracket it is written L, right, in a liquid form. So it's a base. You can see double arrow which gives you H3O plus Cl minus ions. So HCl acid 1. Now HCl will give away its proton. So acid 1 and will give you, in the product form you can see Cl minus ions. So HCl, you can see the arrow, students, it is conjugate acid base pair. So HCl arrow going towards the Cl. So acid 1 base 1. So conjugate acid base pair 1. Similarly, now when HCl gives away the proton, that proton must be accepted by the another. Somebody should be there to accept that proton. So H2O is the base. So base 2 gives you H3O plus ions. So this is an acid. So you can see the arrow H2O going till H3O plus ions. Base 2, acid 2. So this is conjugate acid base pair 2. Conjugate acid 2 base 2 pair. Third, Lewis theory. According to this theory, now let us study what is acid and what is base. Acid, any species that accepts a share in an electron pair is called Lewis acid. And base, any species that donates a share in an electron pair is called Lewis base. For example, now according to this you should have, see students, you should have electron pair, right? Any species that accepts a share in an electron pair, that is acid, and any species that donates a share in an electron pair is a base. So here is the example. You can see ammonia in H3. Ammonia is having a lone pair of electrons. You can see one arrow going towards H plus ions, that is acid. In the another example also, you can see acid and base. So this is acid and base according to Lewis theory. Amphoteric nature of water. Water has the ability to act as an acid as well as base. Such behavior is known as amphoteric nature of water. How it behaves like an acid, like a base. Example, let us take an example. H2O, right? Consider this H2O as an acid. So below that acid is written, and it is in a H2O is in a liquid form. So when you take water plus NH3, which gives you OH minus ions plus NH4 plus ions. We'll take second example. H2O liquid form, but now this time this H2O will act like a base. So H2O plus HCl in an aqueous form gives you H3O plus in an aqueous form plus Cl minus ions in an aqueous form. Now students, observe carefully both the examples when water acts as an acid and when water behaves like a base. There is a difference. And before this, we have already studied the definitions for acids and bases. So H2O acts as an acid towards ammonia and as a base towards HCl. Therefore, H2O is amphoteric in nature. Thank you.